All right, so we left off at 5c. The inverse Laplace of this complicated looking thing. Oops. Okay. We could take the inverse Laplace of each of these terms that are in the parentheses. Those have things in the table that will help us do that. And then in the table, there's an entry for multiplying something you know the Laplace of times e to the something. So let's see, that was 33. Okay. Oh, I hate when it does this. Okay, so here's my table of Laplace transforms. I need an inverse Laplace of e to the something times some stuff I know the Laplace of. So look at this entry. It has an e to the negative as in the Laplace transform. So this is the Laplace transform. I'm trying to go back to the function y. This has an e to the negative as in it. So, yeah, which is the Heaviside function. Yep. How do we do that? Having trouble getting started today. Okay. Oh. Oh, yeah, that's nice. Here we go. The inverse Laplace of e to the negative as times something else is the Heaviside function times a transformation of y. Okay, good. Let's copy that down. All right, so inverse Laplace of e to the negative as times y, right? So this is e to the negative 2s. This whole thing will be my y. So it's going to be the Heaviside function u2, and then times the inverse Laplace of all of that evaluated at t minus a instead of just t. So I need the inverse Laplace of this stuff. So I need the inverse Laplace of all of that. I'm going to evaluate it at t minus a instead of just t. And then I'm going to multiply it by u sub 2. Okay, and that's for the e to the negative 2. All right, so the inverse Laplace of s sub 2, sorry, s plus 2 over s squared plus 4s plus 9, we've done. Right? All right, so this we did earlier in one of the previous parts. So I just need to do this part, the s minus 2 over s squared plus 1. So we should look at the table and see if there's anything that looks like. S minus 2 over s squared plus 1. Well, there's like s squared plus omega squared. So omega could be 1, right? My numerator would have to just be just a plain old s and not an s minus 2. So let's see if I can manipulate what I have into looking like something like this. S over s squared plus omega squared. Yeah, so I'm going to split it into two fractions. The inverse Laplace of s over s squared plus 1 minus 2 over s squared plus 1. Like reverse of adding fractions. Break it into two fractions. Okay, so then I have minus the inverse Laplace of s over s squared plus 1, because I can take each inverse Laplace separately. And then this is minus this whole thing, so it's going to end up being plus the inverse Laplace of 2 over s squared plus 1. Oh yeah, I can pull the 2 out, yeah. All right, 1 over s squared plus 1. Does that have something in the table? Yeah, that would be this one. So omega is a 1, so if I have a 1 in my numerator, that matches that entry of the table. So now I've broken this into 3 Laplace transforms that have entries in the table that I can just pull out. Plus this one, which I did in part B. So inverse Laplace of all right, so this one I did earlier, and it was yeah, something like that. So this is e to the negative 2t cosine root 5t. Okay, so we did that earlier. And then the inverse Laplace of s over s squared plus 1, so that would be s over s plus omega squared. Yes, we do still need to do that, yeah. But this looks like cosine omega t. So this would be, I'm just going to write it down for now, and then I'll account for the shift in the next step. Plus 2 times 1 over s squared plus 1 That's sine omega t. Okay, so that's the whole inverse Laplace of just the piece in parentheses. Okay, so that is just this inverse Laplace. Okay. But what I really need is that inverse Laplace evaluated at t minus a, and in this case, a is 2. So everywhere in here where there's a t, I need to replace it with a t minus 2. So e to the negative 2 times t minus 2 cosine root 5 t minus 2 minus cosine of omega t minus 2 plus 2 sine omega t minus 2. Then I just have to multiply all of that by u sub 2. Oh, and omegas are 1s. Yes, right, thank you. Yeah. So my final inverse Laplace is going to be u sub 2 of t times e to the negative 2 t minus 2 That's it. So it had several steps, but it was all based off of this rule. We wanted to take the inverse Laplace of e to the negative as times y, capital Y, which is a inverse Laplace, which is a Laplace. That's a y of s. So we had to take the inverse Laplace transform of that thing, shift it by a, and multiply by u, by a Heaviside function. For the inverse Laplace? Mm. Mm-hmm. E, it doesn't. But it was e to the negative as, and it becomes u sub a and shifted by a. So it has its influence, but there's no e in the inverse Laplace transform. Oh. That was, so that e came from this inverse Laplace transform that we found earlier. So it wasn't because there was an e in the original problem, it came from here. Yeah. So that is part of the initial question, but the reason there's an e in the answer isn't because there's an e right here. It came from that inverse Laplace transform. Yeah. All right, let's look at D. So calculate the Laplace transform for the solution to the initial value problem. Do not calculate the formula for y of t. Just get the Laplace transform. Okay, so my original problem was y double prime plus 4y prime and y of 0 is 1, y prime of 0 is 2. All right, so we apply the Laplace transform to both sides. So I take the Laplace of y double prime plus 4 times the Laplace of y prime plus 9 times the Laplace of y, and that equals the Laplace of this whole side, u2 times the sine of t minus 2. Is there a 20? Oh yeah, 20. Thanks. Okay, yeah, so now I'm going to need to take this Laplace, do that in a minute. I also need to simplify all these, the Laplace of derivatives, because I have formulas for that. So the Laplace of a derivative is s times the Laplace of the antiderivative minus the antiderivative at 0. So this would be s times the Laplace of y prime minus y prime at 0. That's the Laplace of y double prime. The Laplace of y prime would be s times the Laplace of y minus y of 0 plus 9 times the Laplace of y. And then the Laplace of this guy, u2 times the sine of t minus 2. We should see if there's something in the table that can help me do that. The Laplace of u2 oh, so we got the inverse Laplace of? Yes. Yeah, it's this. It's e to the negative as times y of s. Yeah. Good. So this is going to be 20 times e to the negative 2s times look at this again. Times the Laplace of y, so times the Laplace of sine, right? And what's the Laplace of sine? Sine of 1t would be 1 over s squared plus 1. Yeah. All right, so now I can do another simplification, my Laplace of y prime. So I'm going to have s. The Laplace of y prime is s times the Laplace of y minus y of 0. Then I still have minus y prime of 0 plus 4 times s times the Laplace of y minus y of 0 plus 9 times the Laplace of y. And that all equals this 20 e to the negative 2s over s squared plus 1. Okay, so now I can start plugging in the stuff that I know and combining like terms and stuff. So I know y of 0 is 1 and y prime of 0 is 2. Okay. All right, so I'm going to do some distributing and some plugging in. So y of 0 is 1. So I'm going to have s squared times the Laplace of y minus 1. Y prime of 0 is, yes, thank you, minus s, distributing my s, minus y prime of 0, which is 2, plus 4s times the Laplace of y. Y of 0 is 1, so I've got a minus 4 here, plus 9 times the Laplace of y equals 20e to the negative 2s over s squared plus 1. Okay, so collect all my Laplace of y's on one side. Anything that does not have a Laplace of y, we'll put it on the other side. So I'm going to have s squared plus 4s plus 9 times the Laplace of y equals 20e to the negative 2s over s squared plus 1 plus s plus 2 plus 4, so plus s plus 6. And then divide both sides by the coefficient on the Laplace of y. So we've got the Laplace of y equals 20e to the negative 2s over s squared plus 1 times s squared plus 4s plus 9 plus s plus 6 over s squared plus 4s plus 9. And that's all they asked you to find was the Laplace of y, not y itself. And we actually just did all of the work that you have to do to get that inverse Laplace. Yeah, sure. What do you want to do? Yeah. Okay, can of soda just removed from the refrigerator is 50 degrees, and after 10 minutes sitting in a 70-degree room, its temperature is 54 degrees. Assume that Newton's law of cooling applies. Okay, so Newton's law of cooling says that the rate of change of temperature, which is dt dt, that's the rate of change of temperature with respect to time, is proportional, equals k times something, is proportional to the difference between the current temperature and the ambient temperature. Okay, so my current temperature is, we'll call capital T, and the ambient temperature is 70. And I know that this is a can of soda taken out of the refrigerator, so that I know capital T is going to be less than 70 because it was in the refrigerator. So that's the only reason for doing the subtraction in that order. All right, so write an initial value problem that models the temperature of the can of soda. Okay, so there's my differential equation, and T of 0 is 50 degrees. That's it. Okay, so that's part A. All right, B is sketch the phase line corresponding to the initial value problem and determine the temperature of the can of soda over the long term. Okay, so the phase line is like making a slope field, but compressing it into just one line because all of the slopes are the same on horizontal lines. So I've got a phase line. I'm going to put in any equilibrium points on it. And to find equilibrium points, we set the equation to 0, any place where dt is unchanging. So I set k times 70 minus t to 0, and I get t equals 70. And then I can check on either side of 70. I want to know if dt is, if t is increasing or decreasing, right? So that means is dt positive or negative. So if I plug in a number larger than 70, dt is going to be negative. So it's going to be decreasing. T, the temperature, is decreasing. And if I plug in a number smaller than 70, this number will be positive, k is positive. So dt is positive, which means my function is going to be increasing. Right, it makes sense that 70 is room temperature. If the can of soda is ever below or above room temperature, it comes back to room temperature. So we would call this a sink. So the temperature of the can of soda over the long term, it goes to 70 degrees. So that's B. And then C, how long does it take for the can of soda to reach 60 degrees? So in order to do that, I have to figure out what K is. Okay, so I want to solve this ODE, use my initial value to figure out what K is. Sorry, no, I'm going to use the other, they also gave me after 10 minutes that T of 10 is 54. So I'm going to use that too. Okay, so first thing, I have to solve this. So how do you want to do that? Separation of variables? Yeah, it only has t's on the right-hand side as the only variable, so that might work. T for temperature. So I'm going to divide both sides by 70 minus t. So I've got all my capital T's on the left and little t's on the right. Integrate both sides. So the antiderivative of 1 over t is ln t, but so this is going to be the ln of 70 minus t, yeah. But then I have to account for, if I was going to take the derivative of this ln of 70 minus t, I should land here. But I would have to use the chain rule, and there'd be a negative, so I put a negative in front. So this equals kt plus c. So trying to solve for capital T here, right? I'm trying to get a function for t for time. So I'll move the negative over. That's an easy move. Yeah, well, I could call it a different k, but I want to use the k that was in my original equation. I'd like to know what that is. So I'm going to keep it the same. Okay, so now to undo an ln, raise e to both sides. So I'm going to have e to the ln of 70 minus t equals e to the negative kt plus c1. And e to the ln of some stuff just gives you your stuff, because e and ln are inverse functions. And then this, I'm going to do my little trick here. This is e to the negative kt times e to the c1. And e to the c1 is just another new constant we could call c2. So 70 minus t equals C2 e to the negative kt. And then just solve for t. Add t. Then use your two pieces of given information to find your two constants, your initial condition and your temperature after 10 minutes. So t of 0, if I plug zeros in for t, I get 70 minus C2 has to be 50. So C2 is 20. And then t of 10 is going to be 70 minus 20, just plug in the C2 there, e to the negative 10k, make t 10. And that has to come out to 54. So now I solve this thing for k. So negative 20 equals, oops, negative 20 e to the negative 10k equals 54 minus 70, negative 16. Divide both sides by 20, e to the negative 10k. 16 over 20 is 4/5. Take the ln of both sides. And then divide both sides by negative 10. That's weird. ln of 0.8 divided by negative 10, 0.0223. So my final function is t equals 70 minus 20 e to the negative 0.0223 t. Oh yeah, right. Then they asked us how. Then answer the question. How long does it take for the can of soda to reach 60 degrees? So replace your t with a 60. Solve this equation. You can all do that, yeah. Looks like t comes out to 31.08 minutes. Yeah. Yeah, it was. I like that one. Yeah. Okay, a tank containing chocolate milk initially contains a mixture of 460 gallons of milk, 40 gallons of chocolate syrup. Milk is added to the tank at the rate of 8 gallons per minute, and syrup is added to the tank at a rate of 2 gallons per minute. At the same time, chocolate milk is withdrawn at the rate of 10 gallons per minute. Assuming perfect mixing of milk and syrup, write an initial value problem that describes the amount in the tank. Okay. So the rate of change of syrup with respect to time, the rate of change of the amount of syrup in the tank is ds dt. Rate of change of syrup with respect to time. So this should be the rate in minus the rate out, right? The rate that the syrup's being put in minus the rate that the syrup's being taken out. Okay, so what did they say about how the syrup is being added? 2 gallons per minute. So my rate in is a 2. It's already a rate in gallons per minute. And then at the same time, chocolate milk is withdrawn at 10 gallons per minute, but that's a mixture of milk and syrup. 10 gallons per minute of chocolate milk, but then I need to figure out how much of that chocolate milk is actually syrup. So the amount of syrup over the total gallons in the tank, which is 500. Because they said it's 460 gallons of milk and 40 gallons of chocolate syrup, so it's a 500-gallon tank. So this is 10 gallons per minute of the chocolate milk is leaving, and this is the percentage of the chocolate milk that is syrup. So you can figure out how much exactly syrup is leaving in gallons per minute. So this is ds dt. And then they give us an initial value. The amount of chocolate syrup in the tank at time 0 is 40 gallons. Yeah, they told us that initially we started with 40 gallons of chocolate syrup. So here's my initial value problem. All right, B is sketch the phase line for the initial value problem. Okay, so phase line, first thing you want to put on it is equilibrium points, which we find by setting ds dt to 0. So I'm going to solve this thing for s. So 2 equals 10s over 500. So what? Oh, yeah, I could do that. Yeah. Yeah, I suppose that would have been. So this is 1,000 divided by 10, so s is 100. So here's my phase line, 100. And I know just by common sense that this is probably going to be a sink. But we can check using the equation. Plug in a number bigger than 100, right? So like 500. So I have 2 minus 10, which is negative 8. So ds dt is negative, which means that s is decreasing. So if I plug in a number bigger than 100, s is decreasing. And if I plug in a number less than 100, like 0, make s 0, then I just get positive 2 for ds dt, which is positive. So s is increasing. So I have a sink there. So that means that the in the long term, as t goes to infinity, the number of gallons of syrup in the tank is approaching 100. All right, and then for C, determine how much syrup will be in the tank after 10 minutes. So ds dt simplified is 2 minus s over 50. All right, so I have to solve it. I've got my initial condition, s of 0 equals 40. I have to solve this initial value problem. If I move the s over 50 over, now this is a linear differential equation that is non-homogeneous. So you can solve it using the 3 steps. Find the general solution to the associated homogeneous, guess a particular solution to the non-homogeneous, and then add them together. We have a particular, the equilibrium solution, yeah. So 1, solve associated homogeneous equation. 2, find particular solution. 3, add 1 and 2. So for step 1, I want to solve ds dt equals negative s over 50. Just drop the 2, the associated homogeneous. So this one, I could divide both sides by s, 1 over s ds equals negative 1/50th dt, and solve by integrating both sides. So this is ln s equals negative 1/50th t plus c. Raise e to both sides. So s is some constant e to the negative t over 50. And then step 2, I know that y equals 100 is a particular solution to the homogeneous equation. That's the equilibrium solution. So there's my y particular. So 3, add steps 1 and 2, and I get s, I should say as s particular, because that's my variable. Okay. So s, the general solution, is k e to the negative t over 50 plus 100. Use the initial condition to find the k. S of 0 has to be 40. So k is negative 60. So S of t is negative 60 e to the negative t over 50 plus 100. And then you can plug in the 10 minutes. Plug in 10 for t, and you end up with 50.88 gallons. All right. Y prime minus 4y equals 50 times u2 of t times the sine of 3 times t minus 2. Y of 0 equals 5, and we're supposed to solve this initial value problem. So the existence of the u sub 2, the Heaviside function, means that you're going to have to use a Laplace transform, because we don't have any other methods that can solve a discontinuous forcing function. So I'm going to take the Laplace of both sides. The Laplace of y prime minus 4 times the Laplace of y equals 50 times the Laplace of u2 times the sine 3t minus 2. All right, so what?
If it was like sine of t minus 5 or something, we just not be able to solve that. So the Heaviside has to match.
Oh, yeah, well, no, you would factor out whatever you had to factor out. Oh, well, yeah, you probably couldn't do it. Yeah, it would have to be a t minus 2. Yeah. Okay, so the Laplace of y prime we can simplify to s times the Laplace of y minus y of 0, which is 5, minus 4 times the Laplace of y equals 50 times the Laplace of all that, which we're going to have to do. Yeah, we can get that from the table. Yeah. So yeah, let's write it down. The Laplace of u sub 2 is times the sine of something. So where is that? Here it is. The Laplace of u sub a times a shift of y times t minus a is going to be e to the negative as times the Laplace of just the sine thing. So we can do that. I just looked at the table and I said, oh, if you want to take the Laplace of u sub a times another function, right? Take, it's e to the negative as, so I just wrote down e to the negative 2s, and then times the Laplace of y, times the Laplace of, oh, but, and that's just, right, it's not of the shift though, so it's just 3t, not t minus 2. Yes. I don't know. I mean, I think we derived it once, but I don't remember. Okay. Once you derive it once, you just use the table. Comforted by the fact that you derived it once. Okay, so that came from the table. Taking the Laplace, I was taking the Laplace of u sub 2 times the sine times some y of t minus 2. So in this case, y is the sine of 3t. Okay. All right, so now solve for the Laplace of y. Oh, I need to take the Laplace of 3t too. I'll do that in a minute. So I'm going to have s minus 4 times the Laplace of y equals, I was going to move it over in this step. All right, so now I've got 50 e to the negative 2s times the Laplace of sine 3t. The Laplace of sine 3t sine omega t. So that would be 3 over s squared plus 9. 3 over s squared plus 9. And then plus 5. Then divide both sides by s minus 4. So I'm going to have the Laplace of y equals 150 e to the negative 2s over s minus 4 times s squared plus 9 plus 5 over s minus 4. 3 times 50, yeah. All right, the 5 over s minus 4. Oh, so this is my Laplace of y. So this is like problem mostly done. Now I just have to take it back. Do the inverse Laplace of this stuff. Okay. This is being so good enough. Okay, so y is going to be the inverse Laplace of all this stuff. 150 e to the negative 2s plus the inverse Laplace of 5 over s minus 4. Okay, let's look at the table and see if we can find any inverse Laplaces that look kind of like those things. This one looks simpler, so maybe I'll start with that one. 5 over s minus 4. Well, 1 over s minus a is easy, right? It's just e to the at. So I'll pull the 5 out, and this is going to be 5e to the 4t. S has to be bigger than a. That's fine. Yeah. All right, so that part was easy. And then we have to do the inverse Laplace transform of this other monster. I can. Not out of the Laplace transform. Is that what you meant? Yeah. All right. Let me start on a new page. Okay, working on the harder piece. So I'm going to say this is now going to be the inverse Laplace transform of e to the negative 2s times 150 over s minus 4 times s squared plus 9. And that does look like something from the table. In the inverse Laplace transform area, I have an entry for how to take the inverse Laplace transform of e to the negative as times some other inverse Laplace transform. Okay, so the e to the negative as transforms to a heavy side, and then you have to take the inverse Laplace transform of what's left and do a shift t minus a. In this case, a is, I don't remember, 2. All right, so I need the inverse Laplace of 150 over s minus 4 times s squared plus 9. I need to get that. I need to shift it by a t plus 2. I think it's t minus 2. Because once I do the inverse Laplace transform, there'll be no more s's, it'll be t's. You shift it after you do the inverse Laplace. All right, so first we'll just focus on getting this inverse Laplace. I can. Do I want to? Yeah, I think I'm going to do partial fractions. Because this is a linear over an irreducible quadratic. So I've got 150 over s minus 4 times s squared plus 9 should equal a over s minus 4, a constant over the linear term, and a linear bs plus c over the irreducible quadratic. Okay, so then we solve and we get 150 equals as squared plus 9a plus, and then I'm going to FOIL bs plus c times s minus 4, so I get bs squared plus cs minus 4 bs minus 4c. So my s squared terms are a plus b. That has to be 0. My strictly s terms is just a negative 4b. Also has to be 0. Oh, yeah. And then my constant terms are going to be 9a minus 4c, and that has to be 150. Okay, so this was not set up that nicely for us. A equals negative b, and c equals 4b. So c equals negative 4b. No, sorry, negative 4a. So then over here, I'm going to have 9a minus 4 times negative 4a equals 150. 9a plus 16a is 25a. A is 6, which means that b is negative 6. All right. So now I can take the inverse Laplace transform of a was, what was a? Negative? A was 6? Okay. Okay, so 6 over s minus 4 plus negative 6s plus 24. Okay, the 6 over s minus 4 is easy. Pull the 6 out, and that becomes 6e to the 4t. Let's see, I can pull out a 6 from there, so I'm going to minus 6 times the inverse Laplace transform of s plus 4 over s squared plus 9. This would be an s squared plus an omega squared. So if you could make that an s plus 3 instead of an s plus 4, that would be good. So this is 6e to the 4t. So broke s plus 4 into s plus 3 plus 1. So then the inverse Laplace transform of this guy is in the table. And then if that were a 3 on top, I would have omega over s squared plus omega squared. So I want that to be a 3. So I'm going to rewrite that as 3 over s squared plus 9 and 1/3 in front. Yeah. And then you can pull that out of the Laplace transform. And then this is in the table.